Hi there, in this video clip today I want to talk about the rate of reactions or speed of reactions, i.e. how fast they are, how slow they are. If I took a firework like a banger, there it is, I like the blue touch paper, bang, it goes straight away. Is that reaction fast or slow? The answer is it's extremely quick. If I chucked a piece of any old iron in the garden over a period of time, it turns brown because the iron has reacted with the oxygen in the air and the moisture, the water vapour in the air to form rust. So that reaction would be quite slow. And if I've had too much to drink, self-indulgence I'm afraid, and you wake up, you feel a bit doggo, some of us maybe take a glass of cold water, add a couple of Alka-Seltzer tablets, it fizzes straight away, and gas is coming off that Alka-Seltzer. It's carbon dioxide, by the way. Is that quite quick, that reaction? The answer is it's quite quick. Rate of reaction can be defined in two ways. It's the quantity of product used in time or the quantity of reactants used in time. So it is the rate of reaction is the amount of reactant or reactants used over a period of time, amount or quantity, or the amount of product produced in a certain time. So it's, if I say for example, I've got 46 centimetre cubed of a gas produced in 4.6 seconds. What is its rate of reaction? It's simply 46 divided by 4.6, which is 10 cm cubed per second. Let's take another example. Suppose I say I've got 10 grams of magnesium, say 10 grams of magnesium used up in 100 seconds. So 10 grams of magnesium used up in 100 seconds. Calculate the rate of reaction. Well, 10 grams used up in 100 seconds. That is 1/10, which is 0.1 grams per second. Amount of product in time, the amount of reactant used in time. Now, let's look at graphs or charts of the reactants and the products in a reaction. I'm going now to measure. Rate, by the way, is always to do with time. And suppose I'm taking a reaction which produces a gas. That could be magnesium plus hydrogen. The rate of reaction, the profile looks a bit like that. This is the volume of gas in cm cubed, and this is time in seconds. S. You can see there that the rate of reaction is quickest at the start and it slows down. Let's take the amount of magnesium in a reaction. It's highest at the start, and as the reaction proceeds it's used up. So this would be the product and this would be the reactant. Translating that into simple words, this shows the rate of product produced with time, and this is showing the amount of reactant used with respect to time. I want to look at this graph in a bit more detail. The rate of reaction, I've said it's quickest here and it slows down, and the gradient here is different than that gradient there, and it's the gradient, i.e. the change in this with respect to that, that gives us the rate of reaction, because I've said it's the quantity of product divided by time. Let's put in some actual figures for this now. Suppose that is 20, 40, 60, 80, 100, 120, 140, and I can't count seconds, 20, 40, 60, 80, 100, 120, 140. And let's put in some figures for the volume of gas. 20, 40, 60, 80, 100, 120, 140, right? Okay, I'm going to put them in. 20, 40, 60, 80, 100, 120, 140, 160, 180. Now, suppose I say I want to calculate that rate of reaction. The gradient is equal to up by down, i.e. how much does something go up vertically, or let's change that to across. Let's say I want the rate of reaction at that point there. A tangent is defined as a line which touches a circle or touches a curve but does not cross it. So that would be the tangent. And suppose I say, what is the reaction at that point there? I go down and I go across. The gradient, I've said, is equal to the rate of reaction. How far does that go up? It goes from 100 to 160 is 60. It's going from there to there, and the across is from there to, say, there, which is 40 to 100 is 60. So the rate of reaction at that point there is 60 cm cubed divided by 60 seconds would be 1 cm cubed per second. So that's how I would calculate the rate of reaction at that point there. It's the gradient, distance up by distance across. The things that affect the rate of reaction, we've looked at these before. they are temperature, pressure, surface area of the reactants if it's in a powder form, temperature and a catalyst, and the surface to volume ratio. How do you measure the rates of reaction? Well, let's look at an example. Calcium carbonate or chalk plus hydrochloric acid gives you calcium chloride plus water plus carbon dioxide gas. So I could do this in two ways. I could measure the volume of carbon dioxide produced, the product with reference to time, or the change in weight. And it's this change in weight which I could measure. So if I took something like a flask, like so, and I put it on a scale, I had my marble chips, chalk, it's the same thing, marble chips like that, and I add hydrochloric acid to there, the gas comes off, and if I measured the weight of this, it's going to get less because the gas is coming off. So I would simply measure its weight over a period of time. And if I took the same reaction, this time it's exactly the same reaction again. There's my flask, there's my marble chips, but this time I'm going to add that acid, and I've got a tube coming off, and that is connected to a syringe. And there is my plunger on the syringe. By the way, I'm crap at drawing this stuff. What happens is I add the acid. There's the acid. I've added the acid to the marble chips. The carbon dioxide gas comes off like so. It comes off, and the plunger moves, and I would see the volume of gas there changing with respect to time. So I could follow the rate of that reaction by measuring the volume of gas given off from the reaction vessel in time. And again, the rate of reaction would simply be the weight of or mass of the product, the gas, in cm cubed over time. That would be a second method of measuring the rate of reaction. In that case, it's based on the rate of product, the hydrogen gas produced over a period of time.